In this video, we're going to talk about the Clausius-Claiborne equation. It's an equation that relates the vapor pressure to the liquid temperature, and this is the equation here. Okay, it's the natural log of P2 over P1 is the delta H, or the heat of vaporization, over R, 1 over T1 minus 1 over T2. And what is here is the fact that this is the natural log of P, and this is 1 over the temperature in K. And I want to point out that this, I should have put a parentheses here, this should have a parentheses here. So P2 over P1, you're taking the natural log of that division there. Okay. R is the gas constant, which we talked about in chapter 5. Okay, but this time we're using 8.31, and it's in joules per mole K. Temperature, therefore, has to be in K, Kelvin. And so the delta H must be in joules per mole then. Okay, so these are the units that you have to have for this. So I remember that 2 is on top of 1 and then 1 minus 2. That's just how I remember that. Okay, so let's do a problem. Okay, now I start out all my problems by reading the question and writing down with what the variable is for the question. So it tells me that there's a heat of vaporization that's 16.69 kilojoules per mole. So I'm going to simply write down the formula, or the symbol of that is delta H, WAP, or triangle H, and it's 16.69 kilojoules per mole. I'm going to write down the fact that I have a temperature, because it's degrees C is temperature. That's a negative 18.7 degrees C. I have a pressure of 92.44. That's in millimeters of mercury. It wants me to calculate, so it's important not only when I'm making this list to find out what it is I want. I want the pressure when my temperature is equal to 2.7 degrees C. Okay. So the formula is the natural log of P2 over P1 is delta H of vaporization over R over 1 over T1 minus 1 over T2. Okay? So as I went through this, the delta H has to be in joules. So I'm going to simply, there's 1 times 10 1 times 10 to the 3 joules per 1 kilojoule. That's all the way back in chapter 1. Means that I have 16,690 joules. The temperature has to be in Kelvin, so I'm going to add 273 to this. And when I do that, I get 254.3 K. This also has to be in Kelvin, so I'm going to add 273 there. And that gives me 275.7 Kelvin there. And this R here is the gas constant of 8.31 there. Okay, so it's a constant. Alright, so now I'm going to start. It's easier when I'm solving for pressure, it's easier to solve for P2 than P1. Numerically, it doesn't matter. You can do either one. Okay, I do need to assign, so because of that, I'm going to make my unknown 2, and therefore my known is 1. Okay, you can solve it such the unknown is 1. It just makes it a little bit harder mathematically. Okay, so I'm going to have natural log of P2, which is what I don't know, over P1. P1 is 92.44. My delta H of vaporization is 16,690. R is that constant of 8.31. My first temperature is the 254.3. My second temperature is that 275.7. Okay. I can't, this is inside the parentheses, so I can't take a natural log. I can't do anything to this side until for a little bit, so I'm going to leave it the same. P2 over 92.44. So I'm going to simplify this side. When I divide 16,690 by 8.31, I get 2008.42. Now, I do this as one mathematical operation. So I'm going to enter it and then I'm going to show you. Well, maybe I can do it this way. I don't know if you can see this. This is going to be hard for me to see. So I type in 254.3 and then this x to the minus 1, or some calculators has it as 1 over x, minus 275.7. Oops. Delete. Okay, and again, this x to the minus 1. So I can do this whole parentheses in one very simple calculation. Okay, and I get this 0.0003052 Most of the time I want answers to 3 significant figures, so I tend to carry at least 4. So there's my 4 significant figures. Again, I still can't do anything to this side, so I'm going to take natural log of P2 over 92.44. Now I'm going to multiply my 2008.42 times that. So times 2000, I'm doing it like I don't have it written down. Okay, I do. I get 0.6130. Okay, so I've simplified that side as much as I can. So the next thing I'm going to do, the only way to get rid of a natural log, because I can't do anything with inside the parentheses without getting rid of the natural log, is to take the anti-natural log, or e. And I need to do that by both sides. So e is anti-natural log. E is times 10. So they're not the same thing. And so on your calculator, okay, if you look at the natural log, if you look at the blue above that, you see that that's e to the x, and that's the button that I push. So when I do that, it gets rid of the natural log, so I'm just left with P2 over 92.44. But when I do it to this side, I get 1.846. And now I need to solve for P2, so P2 is 1.846 times the 92.44, and I get 170.6 millimeters of mercury. I want to kind of make a little bit, see if this makes sense. This is a higher pressure than the 92.4, so temperature 2 should be higher than temperature 1. And temperature 2 is in fact higher than temperature 1. So when I'm comparing this to that, temperature 2 is higher. Okay? So, and don't forget your units when you're answering. On the next video, we will do an additional problem with this.